Okay, so good afternoon, everyone. My name is João. I'm a PhD student from Lisbon, and today I'll be presenting you pretty much what my PhD plan is all about. Okay, I should, of course, tell you what my PhD plan is all about, which is extending the stochastic titration constant CpHMD method to the AMBER14SB force field for enhanced drug discovery. Okay, so first things first, I wanted to introduce to you the biological idea behind my project, and this is basically what got me my grant. And this is, we're working on studying the acid sensing ion channels, or ASICs, just like the shoes. And these are voltage independent transmembrane channels, cation channels, that open upon the exposure to lower pH values. And they play in a plethora, and they have a role in a plethora of not diseases, but of conditions. And one of them is nociception, which for those of you that don't know is the perception of pain. And this is why we thought of using this family of proteins to target for the discovery of new analgesics. Okay, so what we want to understand? We want to study the effect that the pH has on each of the ASIC subunits, as these proteins are made out of 3 subunits, and we want to study the ASIC's inhibition at different pH values so that we can really understand what is happening in this process. Okay, and the best tool to do this is, of course, to do constant pH molecular dynamics. We want to take into consideration pH in our simulations. And since we are talking about ion membrane transporters, the force field that has shown the best performance in mimicking the experimental data to do this is the AMBER force field. So, of course, we want to make an extension and to consider and use this force field. Okay, this is very basic to most of you and pretty much to all of you, I'm sure. But what changes with pH and why we want to take into consideration pH are the tritratable amino acids, which change their protonation state depending on the pH and depending on the conditions. And I'm only really showing you this slide as a provocation to the AMBER people, because one thing, if you notice, the side chains of our amino acid, the titratable part of the side chains, is very similar to the main chain. So we not only want to have the titratable amino acids, we also want to consider and have the N and the C termini titrating as well. Okay, so for amino acids, we know that if the pH is smaller than the pKa, then we have a protonated form, and if the pH is larger than the pKa, then we have a deprotonated form. And the pKa is nothing more than the pH at which the concentration of the protonated form is exactly the same as the concentration of the deprotonated form. And so this means that if we have the pKa of the different residues, we're able to predict or to predict what would be the protonation state of the different residues. And this allows us to do very neat titration curves, which we basically allows us to see at the given pH what is the protonation state of the given residue that we're taking into consideration. And that basically what we see is that as pH increases, we go from a protonated state to a deprotonated state. Okay, there is a small caveat to all of this that, of course, is that we cannot define pH in the simulations normally. It's not a parameter that we usually use like temperature. So how do we simulate things at constant pH? We define and we have the protonation states changing with time. And this is the main difference to the conventional MD, which has fixed protonation states, which are predicted at the beginning and are kept constant throughout our simulations. Okay, so now stochastic titration constant pH, molecular dynamics. I know that Miguel has talked to you about this a little bit in the morning, and I'll just try to be as brief as I can because you've already heard about this. But we have a cycle where we basically predict and we do energy calculations using Poisson-Boltzmann, which are then used in Monte Carlo to sample the different protonation states. And as we change the protonation states of our system, we then use MMMD of the solvent to relax it a little bit, and then we do MMMD of our full system to then have a new conformation that will then be fed to the Poisson-Boltzmann, so then we can repeat the cycle iteratively for as long as we want. And we've been successful in a plethora of different systems to mimic experimental data. In black, we can see the experimental titration curves for this specific protein. And in blue and in red, we can see the different forces that we already support, so Charman Gromsch. And we can see that it mimics, we've been able to mimic pretty well the experimental data. And even for the systems where you don't have the full titration curves of the proteins, we've been able to predict more or less well the isoelectric point of these different systems. And even in more difficult cases, this is a very well-known case, the case of the glutamic acid 35 of the lysozyme. It has a very shifted nature. And its pKa, experimental pKa, is 6.2. And with both the implementations of the 2 different forces that we have, we've been able to mimic it quite well. However, not everything is sunshine, and Miguel has talked a little bit about this in the morning, and a specific case where we were not able to actually have it predict correctly the pKa's in this specific case of these cysteines, where by nature, cysteine 32, as we can see here, it has an experimental pK of 7.2 or 7.1. And this means that there should be a cationic interaction making this pK shift to a smaller value than usually the cysteine in a well-surveyed environment is. However, as we can see, the Gromos implementation has been able to get closer to the experimental pK value, whereas the charm appears to be a little bit of a constraint and not allowing for a faster sampling and having it closer or getting closer to the experimental data. Okay, so currently our method, the stochastic titration CpHMD, supports Gromos and the Charm family of force fields, and it's now in the process of supporting AMBER14SB. And once we do this, we'll finally be able to have a method that we can compare the different force fields for the different systems and see which one is more appropriate to what kind of system. For this is it's a good reasoning for why we want to do this. Okay, but this is obvious for you if you know. If you don't know now, you know. That is that Amber has already a native constant PHMD method. So why are we wanting to do this and we just don't compare our methods to the Amber native one? And a very big difference is that stochastic titration uses constant PHMD, uses Poisson-Boltzmann to obtain the free energies, whereas the Amber constant pH uses generalized Born. And this means that we have a focusing step on the residue sidechain on our method that doesn't happen in the Amber method. What this basically means is that when we are titrating residues, the only thing that titrates in our method is the sidechain of the different residues, and in Amber, the whole residue titrates. And also, our method runs in Gromax, and of course, the Amber native one runs in Amber. Okay, so these were the objectives of my PhD so far. But before being able to study and to look for these analgesics and study the biological system, we need to first extend the stochastic titration and having it support the AMBER14SB. And now, these are a few of the steps. We've been able to create the titratable residue blocks for the different charge chain with different charges, and I will get to that in a bit. And we've now tested this new implementation with dipeptides, and this is something that I will also show you. Okay, so first things first, why do we need to change Amber? Or now I'm spoiling you, we need to change Amber. And the reason for this is that we have charge propagation going from the side chain to the main chain. And because we use Poisson-Boltzmann, as I told you, it focuses only on the side chains. This means that we have to have the entirety of the charge of our residue in the side chain. So what we had to do was we need to get some charge out of the C beta and the hydrogens that are linked to it, and then have it transferred to the C alpha and the HA. And this has allowed us to localize the charge where we need it to be for the Poisson-Boltzmann calculations. Also, as if this wasn't enough, all the different titratable residues have different main chain charges. So we had to do this differently for the different residues. However, the main chain charge propagation is not that big. As you can see, for most residues, the largest one is minus 0.14, which is for the aspartic acids. And this is the same case because Amber has blocks for when the residues are in the C and in the N termini. And this is the same case for when these residues are in the termini. Okay, so another thing that we had to do, so another approximation that we had to do, of course, we need to verify that we're not ruining everything by doing all of these approximations, was we needed to, for simplicity reasons, we needed to average out the charge and basically create a block for the termini. So if we didn't create a block for the termini, when we have the titrating termini, we would have to define the charges of the protonated and for the deprotonated form of every residue in the N and in the C termini. And this would be way too much work. So a very simple, or an approximation that we did, a simplification that we did, was to create a block for the N and the C termini. And to do this, we averaged out the charges across all of our residues for the different parts of the main chain. And because we want to have the charge very well localized, we also made an adjustment again to the C alpha and to the HA to make sure that the total charge was as we intended it to be. And we did this for all of the different residues in this N termini for this specific example. Of course, because we are changing the charges now in the main chain, we need to make sure that we have neutral amino acids, for example. Or we have for the N termini, we need to have amino acids with charge 1. So we also apply the correction to the C beta once again. So basically the same thing. And now we have these different blocks for the N termini. And of course, since we did this for the N termini, we did exactly the same thing, but for the C termini and for all of the different residues. Okay, so now I've shown you what we had to do to get, of course. How do you what? Sorry? Yes. we distributed evenly between the C alpha and the HA, so the hydrogen that's linked to the C alpha. We split it in half. Yes, exactly. Exactly. Yes, that's what I will show next to see if everything's okay. Yes. Okay, so another thing that we had to do, so we need to have the charges for when we have neutral N and C termini. And the best place to get this was for the neutral N termini, we went to the side chain to the amine group on the far end of the neutralizing block that we already have in AMBER parameterized. And we use these charges. And for the neutral C termini, we use the neutral aspartic acid at the end of the carboxylate group. So now the part of testing if everything's okay, we use these combinations of dipeptides so far, where we have a combination of the different titratable amino acids, both in the N and C termini and in the middle of a protein. And since we are changing the charges of the N and C termini for every residue because we're making that average approximation, we also tested a dipeptide in which we did not have a titrating residue. We only have alanines. Okay, so we used the two different charge sets, so the default one and the changed one, and we used three triplicates of 100 nanoseconds each with using GROMACS and PME, and we did almost the same setup using AMBER, but since we did the GROMACS simulations first, we could not use exactly the same parameters as we used in AMBER, in GROMACS, sorry, because AMBER does not support the thermostat, the Viry scale, and the barostat, the Parinello-Hamann, so we had to use Langevin and Nose-Hoover for the AMBER simulation. So the AMBER simulations are slightly different, but we are using the same charge sets, just with this, but it's something to keep in mind for when we analyze the results. Okay, so these were all of the analyses that we thought of to analyze to see the impact of these different charges that we used. And same thing to start with, I want to show you some conformational analysis for all of these. And as we can see here, the thing that I want to take out from this is that in blue we have the change charge set, which I called constant pH AMBER, and in brown we have the default charge set, which I call the default AMBER. And for all of these different conformational analyses, what we can see is that the blue and the brown line pretty much overlap with each other. And this is what we were expecting to see. We do not want to see artifacts rising up from the new charges that we created. For example, it would be worrying if there were to be a new peak here where there shouldn't be any sampling from the default charge calculations. And we do this for the different analyses, and we see that there's a very good overlap between the two things, the two charge sets. And these were the GROMACS simulations that I showed you. And in AMBER, exactly the same thing happened. So we have a very good overlap between the two different charge sets. Okay, moving on to the energies and not structural analysis. Now I show you the energies. And we look for the potential energy in vacuum, so only of our systems, only taking into consideration our proteins. And we can see that once again, there is a small shift, but it's a very small shift, and the distributions are very similar for the dipeptides that we've done the calculations for. And this is such a small system such a small shift that when we take into consideration the entirety of our solvent, the entirety of our simulation, so basically doing the energy calculations, but considering the waters, the shift completely goes away and it gets lost in the middle of the natural fluctuations of our system. So we're happy with this, and this was the case for the simulations in GROMACS, and the simulations using AMBER, they show more or less the same profile. So this is something that we were happy to see that it was not taking that much of an impact on. Okay, so this is what's ongoing, and these are the next steps for this work. We want to have our old version of the code for simulating stochastic titration constant pHMD. We want to have it support, and we want to have it supporting also CpHMD. I had these slides prepared before knowing what Miguel was going to talk to you about. So now that I know that Miguel has shown you what CpHMD is, basically we have a Python wrapper that speeds up the sampling process of the protonation states, and it's already available for you to use if you wish to do so. So this is more advertisement for you. And of course, we now have CpHMD, which basically takes into consideration PyPK to do these simulations of constant pHMD. Sorry? Okay, so after having analyzed and looking into all of these different properties of the dipeptides and making sure everything was okay, we're now looking into moving on to other systems, to test systems, and these were the test systems that we used for our CHARM implementation. We're looking forward to doing the same thing and looking into the specific cases that we analyzed for the CHARM paper. And of course, we want to use other proteins as well. If you have any ideas, I feel like this is the perfect platform to ask for this. If you have any ideas of other test systems that we should consider, please talk to us and let us know. And of course, we'll do this using CpHMD, so using constant PHMD, to make sure that we are sampling the protonation states and the pKa correctly of the different residues. And we also, because we're changing the charges, right? So we need to make sure that the structural, for example, the secondary structure of our proteins is healthy. So what we intend to do is to do long simulations of different test systems as well. Once again, if you have any idea for good test systems, please talk to us. And we want to do these long simulations to see if everything's okay. And with this, I finish my presentation. Thank you very much for your attention. And if you have any questions.
With the charges has been known for a long time. So in the AMBER stochastic constant pH implementation or hybrid MCMD implementation, they absorb the charge to C beta atom, I believe, and we follow that recipe as well. So, but you are spreading on every single atom. That's what you're saying, right?
What do you mean by spreading? Spreading the charge?
Yeah.
No, we're just changing the C betas, the hydrogens linked to the C beta.
Oh, okay. So yeah,
we're keeping it as localized as we can.
Right. So what I'm trying to say is that people have done it. Perhaps you could compare with others.
Okay.
That's one question. Second comment.
Who has done it? Do you know?
Second comment is what?
Who has done it?
Oh, Mongan.
Okay.
JCC 2004, around 2004. Okay. Yeah, and we also done it recently, 2018.
Okay.
2019. So secondly is for your validations, the constant pH validation studies. You can look at other more challenging proteins. So base 1 is a good system to look at whether you can get the acid base correctly.
Okay.
And in staph nuclease, there are 2 couples residues, ASP19 and 21. Make sure that you can get the acid base components right.
Okay. Okay. Thank you very much.
Any more questions? If not, then thanks again, the speaker. And let's come to the